Good morning, I am Renu Sharma, Assistant Professor, EC Department. Today I am going to start with the next part of Unit 4, that is related to different types of sampling. So, in the previous lecture I have discussed about ADC, that is a kind of digital transmission technique, analog to digital converter. So, it consists of different steps, like first one is the sampling, second one is quantization, third one is encoding. So, in this lecture we will discuss different types of samplers or the different types of systems that are available that will perform the operation of sampling. So, in this case the input signal is basically, it is analog in nature, it will be applied to a multiplier where it will be multiplied by a series of impulse function. Now, this impulse function is been defined at different time instants, like it will be defined at 0, t, 2t, 3t. So, at every t second this signal will be defined. This signal will be defined and it will going to, this will be multiplied by the input signal, that is nothing, it is a message signal. Now, these two signals are multiplied together to get a signal that is yt. So, that will be the sampled version. So, this is a kind of ideal sampling only, because the width of the signal, that is the impulses, will be tau, which tends to 0. This tau tends to 0. So, that is the case for ideal sampling. Practical aspects of sampling and recovery. In practice, the sampling of an analog signal is accomplished by the means of high speed switching transistor circuits. The resulting waveform deviates from the ideal form of instantaneous sampling, because the operation of physical switching circuit, however fast, still requires a non-zero interval of time. So, we often find that samples of an analog signal lengthened intentionally for convenience in transmission. So, we wish to evaluate the effects of these practical deviations from the ideal conditions. So, this is the first kind of sampler, that is natural sampler. Now, the input to this sampler will be a signal, that is GT. It will be this, there is a simple switch is there which will going to operate on this clock pulse, which is nothing, it is a carrier signal. Now, whenever the amplitude is high, this switch will be closed and whatever is present at the input side, it will be available at the output side. And when this is low, then the switch will open and we will having the 0 value. So, this is how this sampling will be there. So, in case of this natural sampling, as you can see that there exists a width of the pulse, that is denoted by tau. So, tau tends tends to 0. So, this is the input waveform that you want to sample. This is the signal, that is train of pulses, and this is how the sampled signal will looks like in case of natural sampling. So, ordinary samples of finite duration. Now, next one is the natural sampling. So, analog signal applied to a switching circuit controlled by a sampling function. So, that consists of infinite successive rectangular pulses of amplitude A and duration t with a period of ts. So, that is the sampling time. So, you can see that this is how the signal will looks like, and when you are going to derive the equation, it will be st is equals to ct into gt. So, that will be the carrier signal multiplied by the input signal. So, the natural sampler provides the sampled signal, which is denoted by st. So, when ct goes high, this switch s will be closed, therefore, st will be equals to gt. So, when ct is plus a, which means that when the amplitude is plus a, the switch will be closed and output will be equals to whatever the input is. Now, next is when ct is equals to 0, then the switch will be open, then st will be equals to 0. Natural sampling is it is continued when we are going to derive an equation like st is equals to ct into gt. So, ct is basically, it is a represented, it is a continuous time signal which will be represented by a train of box filters, box waveform, box gates. So, that will be denoted by sinc function in case of time domain when we are doing the Fourier series transformation when we are representing it using Fourier series. Now ST is nothing, it is the sampled signal. Now this will be the signal which is converted from time domain to frequency domain. So this is the ordinary samples of a finite duration where SF is equals to Fs t into a summation n is from minus infinity to infinity sinc and Fs t gf minus nfs. So illustrating the effect of using ordinary pulses of finite duration, the spectrum of the sample signal is given by this particular type of waveform, which is a kind of triangles denoted at generated at Fs to Fs 3 Fs and so on. Next is natural sampling continuum. The relationship between the spectra GF and SF is illustrated in the particular diagram. So assuming that GT contains no frequencies which is lying outside the band from minus W to plus W, that the sampling rate Fs, it is greater than the Nyquist rate, that is 2W. So that there is a case which is known as aliasing. So we see that the effect of finite duration of sampling pulses is to multiply the nth lobe of the spectrum by TA by TS sinc and FST. The original signal GT can be recovered from ST with no distortion by passing this ST through an ideal low pass filter with bandwidth P. So for this case we have to consider a condition where AT is equals to 1, so that each rectangle pulse of the sampling function CT has a unit area. So then comparing this equation with equation 4.6, we can see that pulse duration T approaches to 0. So there are three different types of sampling. Like in case of this ideal sampling, this tau tends to 0. Next one is the natural sampling when the pulse is tau, and third one is the flat top sampling where the top of each of the sampled pulse will be flat, and again its width will be tau with whatever signal we are multiplying. So this is the case of ideal sampling. Now this signal is nothing, this is the sampling process, that is analog signal. This is instantaneously sampled version of the analog signal. So this will be a sampled version. This equation is multiplied by this one. This is GF, which will be considered as the frequency domain representation of this one, which will be extended from minus W to plus W, and then it will be extended from this one. So the spectrum of this first one is the band limited signal, and this B is the spectrum of the sampled version of GT for a sampling period of TS, which is equals to 1 upon 2W. So flat top sampling is there. Consider the situation where the analog signal is sampled instantaneously at the rate that is denoted by Fs, which is equals to 1 upon Ts, and that the duration of each sample is lengthened to T as it is shown in the figure next. So using this ST to denote the sequence of flat top pulses generated in this way, ST will be is equals to summation n is from minus infinity to infinity G and Ts HT minus NTS. So what is GT? GT is nothing, it is the input signal, and it has been performed convolution with the filter which is HT minus NTS. Now flat top sampling, in this case, as you can see, the sampled signal is having the tops which are flat. So this is flat top sampling, this is TS, this is T, and the figure is flat top samples are there. So this is how this HT signal is there. So HT will be 1 for the interval from 0 to T, and it will be 0 for T is less than 0 and T for T is greater than T. So that is the representation of this particular filter. This is HT, its equation will be summation n is from minus infinity to infinity G and Ts HT minus NTH NTS. So, from the instantaneous sampling, as you can see from the previous equation, that is G delta T is equals to summation n is from minus infinity to infinity G and Ts delta T minus NTS. So, we can perform the convolution of this with the pulse HT. We will get G delta T multiplied by HT, that is performing the convolution. So, G delta tau HT minus tau d tau, this is the operation of convolution. Then when we are going to put this value of G delta T from this equation, we are having this, that is integral and summation G and Ts delta tau minus NTS HT minus tau d tau. So, which will be equivalent to summation n is from minus infinity to infinity, and we can perform this particular operation, that is solving the equation. We can integrate this particular value and we are going to perform the summation on this G and Ts. Then from the shifting property of the delta function, we have this G delta T convolution with HT is equals to summation n is from minus infinity to infinity G and Ts HT minus NTS. So, ST will be is equals to G delta T convolution with HT, and SF is equals to G delta F into HF. So, this is how the convolution is being done, and we can put the value of G delta F from the previous equation, that will be equivalent to this one, that is Fs summation m is from minus infinity to infinity Gf minus mfs into Hf. Now, given this formula of SF, how do we recover the original message signal? So, since we are having this particular signal equation of SF, how we can reconstruct the original signal from this one. So, GT is basically strictly band limited, and that the sampling rate Fs is greater than the Nyquist rate. Then passing this ST through a low pass reconstruction filter, we will find the spectrum of the resulting filter output is equals to GF into HF. So, this is equivalent to passing the original signal through a low pass filter of transfer function HF. Now, when this has been passed through HF, so HF will be equivalent to T sinc function of Ft e to the power minus j pi f into T. So, this is the condition for HF mod, which is the sinc function, and this is the rectangular pulse of HT, and this is the spectrum of HT. That will be argument of HF versus F graph. As you can see that this is linearly decreasing graph. So, that is the case for flat top sampling. So, by using the flat top samples, the amplitude distortion and delay of T by 2 will be introduced. This effect is similar to the variation in transmission with frequency, that is caused by the finite size of the scanning aperture in television and fax. Accordingly, the distortion caused by lengthening the samples is referred to as aperture effect. So, that is a very important effect that we have to consider in case of flat top sampling, that is aperture effect. So, how we can correct this aperture effect? Now, this effect is being corrected when we are using when we can use an equalizer in cascade with two reconstruction filter. The equalizer has the effect of decreasing the band pass or band loss of the reconstruction filter as the frequency is increasing. So, the amplitude response of the equalizer is given by 1 upon HF mod is equals to 1 upon T sinc Ft, which is equals to pi f divided by sinc pi f. Now, this is flat top sampling, rectangular pulse sampling. Distortion introduced by the flat top sampling causes loss of high frequency information. So, this is because the input signal may be changing while the sample signal is held constant. This error can be readily observed in both the time and frequency domain. So, this error or noise can be reduced by reducing the aperture width. Now, you can see that this is time versus domain versus time. This is aperture error, this is sampling waveform. This will be the frequency domain, This is aperture error. This is sync envelope, which is the demodulated signal. Now next is sampling and hold circuit for the signal recovery. So this is very important thing where we are going to see that sample and hold circuit is also there to take the samples of the signal. So this is a very simple circuit. As you can see that there is an amplifier connected at the input side, then there is a simple switch and connected with a capacitor. So the sample and hold circuit is this one. This is the idealized output waveform. Now you can see that the staircase kind of waveform will be generated, and by connecting the starting edge of each pulses, it is we can going to generate the input signal, and this will be the output ut. So the sampling and hold circuit for the signal recovery is ut is equals to summation n is from minus infinity to infinity g and ts ht minus nts. So where ht is an impulse response representing the action of the sample and hold circuit, that is ht is equals to 1 for t is from 0 to ts and 0 for t is less than, which means that this will be the waveform of ht from 0 to ts. Its amplitude will be 1, this will be ht, and outside this the amplitude will be 0. Correspondingly, the spectrum of the output of the sample and hold circuit is given by this equation, that is uf, that can be calculated using the frequency domain of signal ut. So where gf is nothing, it is the Fourier transform of the original analog signal. Now this is given as the hf, which is the transfer function of the filter that we have used. Now this is sample and hold circuit for the signal recovery at the receiver side. So the components of this signal reconstruction filter is having a sample waveform, that is sample and hold circuit, and it is passed through a low pass filter. Then there is an equalizer that will going to equalize the waveform that whatever we have generated. Thank you for today's lecture.